So, good morning, everyone. So, once again, welcome to Physics by Physics. And in this C.T.P series, I will take some question based on electrostatic potential. And again, we will take questions from our QIP file. And we will see how to solve questions related with electrostatic potential. So, let's start. So, electrostatic potential, and we have summarized last 15-year questions of different exam related with electrostatic potential. So we will take questions only related with electrostatic potential. So let's see what are the concepts that we are going to use. Electrostatic potential. So I will give you summary of this topic, whatever be the important result and formula that you have to remember. So you should remember it. So you know that electrostatic field is conservative in nature. So first thing is curl of E is 0. Electrostatic field is conservative in nature. Field is conservative in nature. And you know the property of conservative fields that curl will be 0, line integral is independent of path, closed line integral will be 0. So you will see in electrostatic field A to B, E dot dl will be, this is independent of path. This will be independent of path. Independent of path. And you will see closed E dot dl is always 0. These are the properties of electrostatic field. And you will also see work done is independent of path. It only depends on potential difference between 2 points. So if you have to check whether the given field is electrostatic or not, you have to check for curl of E. Then one relation is E can be expressed as minus of gradient V, where V is the electrostatic potential. Potential at a particular point is given by minus, I am taking infinity to be a reference point, where we are assuming potential is 0. So this will be given by E dot dl. This will give you potential at a particular point. And then if you have to find potential difference between 2 points, this is minus A to B E dot dl. This is potential difference between 2 points. Clear? So we are going to use these results. If you have continuous charge distribution, please note it down. Now, potential for a continuous charge distribution is given by 1 by 4 pi epsilon naught integral dq by r distance away from any continuous charge distribution. Now, when you have a line charge, we will write dq as lambda dl. Then this integral will be a line integral. For surface charges, dq will be sigma dA. And for volume charges, it is given as rho d tau. So accordingly, this integral may be a line integral, surface integral, or volume integral. So you have to remember these results if you want to find the electrostatic potential in different configuration. Clear? So now let's take some examples. Now let's see. I am taking question number 1. Consider an electrostatic field in a region of space. Identify the incorrect statement. So first is work done in moving charge in a closed path inside the region is 0. Yes, because it's a conservative in nature. So in closed path, when you return to the same point, potential will be same. The curl of E is 0. Correct. The field can be expressed as a gradient of some scalar. And potential difference between any 2 point in the region is always 0. No, this is incorrect. Whenever there is an electric field, there will be potential difference. So option D is incorrect. Clear? So sometimes question may be asked based on the statement. So if you know the result, you can easily identify. Now take next question. I am taking identical charges Q are placed at 5 vertices of a regular hexagon of side A. The magnitude of the electric field and the electrostatic potential at the center of the hexagon are. Let's identify correct result. So now take question number 2. So let's see. Consider this one. And this will be the center. And I'm taking, this is charge Q. This is another charge Q here. This is another charge Q. So there are identical charges Q are placed at the 5 vertices of a regular hexagon of side A. This side is A. Sides are A. So what will be the potential at this point? Potential is simply scalar value. It's a scalar value. So because this distance will be also A. These distances are also A. So what will be potential? Potential will be given by scalar sum 1 by 4 pi epsilon naught Q by A, and then because there are, you have to multiply with 5. So this is 5Q by 4 pi epsilon naught A. And what about the electric field? Electric field, you have to see the vector sum. So if you see field due to this and then field due to this, they are in opposite direction. Now, if you are taking field due to this, in this direction, and then you have a field, you will get field due to this particular charge only, because these field will cancel each other because they are symmetrically placed, both are positive. So field will be away from these charges. So at this point, electric field is given by due to single charge. Direction is not given. You know the direction also. So magnitude of the electric field is given by 1 by 4 pi epsilon naught Q by A square. You can easily see what will be the electric field and potential. Now see the next question. Let's see next question. See next question. Now consider question number 3. So here in this question, option C is correct. Option C will be correct. Now you have question number 3. Question number 3. So you have a hollow spherical shell which carries charge density rho is k by r square in the shaded region. Then find the potential at the center. How you will get the potential at the center? So if you know electric field in different region, only then you can write the potential. So we have to first write the electric field in different region. So let's see how we will write the electric field. How we will write the electric field in different region. So this is the shaded region. This inner radius is A, outer radius is B. So using Gauss law, you can easily write. So let's see R less than A. If you draw any Gaussian surface, charge enclosed will be 0. So I'm directly writing this because charge enclosed in this region will be 0. But if you will write in a region R2B, so in this region, let's say electric field is E2, left hand side mod 4 pi r square. I'm using Gauss law, closed E dot dA, closed E dot dA is equal to Q enclosed by epsilon naught. So in a spherical symmetry, I'm taking any point in this region. Let's say this point P is R distance away. So you have to draw a Gaussian. This will be the Gaussian surface. So charge enclosed is 1 by epsilon naught rho d tau. Q enclosed is where Q enclosed is given by volume integral rho d tau. And since rho is function of R, so we can easily write this as K. Let's take it as some new variable R dash square. And this is 4 pi R dash square dr dash. D tau will be this. And R dash varies from, you have to find charge enclosed within the Gaussian surface. So this will be A to small r. So that will give you the electric field. Now see, this will give you 1 by epsilon naught 4 pi k r minus a. So this 4 pi will cancel out. E2 is given by k r minus a by epsilon 0 r square r cap. This is the electric field in region 2. In same way, we can find the electric field in region 3 also. Let's say now this point P in region 3. Again, you have to draw a Gaussian surface. So for R greater than B, we can write mod E3 into 4 pi R square. I'm applying Gauss law for region 3, 1 by epsilon naught. And this is K by R dash square 4 pi r dash square dr dash, and limit will be r dash will be from A to B, because if you are considering a Gaussian surface for outside point, total charge will be in the region A to B. So this will give you 4 pi k by epsilon naught B minus A. So electric field E3 will be given by 4 pi will cancel out, k times B minus A epsilon 0 r square r cap. This will be the electric field. So first you have to find the electric field. So if you know E1, E2, E3 in different region, now you can define potential at the center. So till now I have just applied the Gauss law and I have calculated the electric field. Now you have to find the potential. If you know E1, E2 and E3, now we will write the potential. So note it down. Now see, what will be potential at the center? Electric field we have already calculated. So now by definition, potential at the center is given by minus infinity to 0 E dot dl. Let's see how we will apply the formula. That potential at point R is minus infinity to R E dot dl. But now potential is at the center. So R is 0. So when you integrate from infinity to 0, you will encounter 3 different regions. Accordingly, you will write this as first minus infinity to B E3 dot dl. Then minus B to A E2 dot dl. And then minus A to 0 E1 dot dl. First infinity to B E3 dot dl, B to A E2 dot dl, B to 0, A to 0, B to A, then A to 0. So because electric E1 is 0, so this term will be 0. Now see, I will write minus infinity to B. Now dl is in the direction of r cap, radial direction. So dot product will give you 1. So if you see E3 is KB minus A by epsilon 0 R square TR. And then B2A, E2 will give you K R minus A by epsilon 0 R square dr, and third term will be 0. Now this will give you minus K B minus A by epsilon 0 1 by R square is minus 1 by R infinity to B. Now it's a matter of calculation. So let's see how we will integrate it. And this will give you minus K by epsilon naught common. Now first, this will give you 1 by R. So this is ln R. And then you have plus A by R. And limit is B to A. So now this will give you K B minus A by epsilon naught B. Minus minus plus 1 by infinity will be 0. And this will give you minus K by epsilon naught ln A minus B. So this is ln A by B plus A 1 by A minus 1 by B. Okay. So now this will give you KB minus A epsilon naught B. This will give you minus K by epsilon naught ln A by B. And this is B minus A minus K by epsilon naught B minus A by B. So just see, this will cancel out, and you will get K by epsilon naught ln, because this is you have to write in terms of B by A. So what will be B by A value? K by epsilon naught ln B by A. So this will give you K by epsilon naught ln B by A. Now this is the potential at the center. So option C is correct. Minus A by B is minus ln A by B is ln B by A. So in this case, answer of question number 3 is option C is correct. So first you should know how to find the electric field using Gauss law, and then you have to apply potential at any point, taking infinity as a reference point. So whenever charge is localized in certain region, means it is not extending itself to infinity, your reference point will be infinity, because then potential will be 0. But if charge itself tends to infinity, then we have to take some arbitrary reference point. So you should remember this point. Okay. Now let's see question number 5. Yes. See question number 5. Now you have two uniformly charged insulating solid sphere, means it's a dielectric spheres. Sphere A and B, both of radius A, carry total charges plus q and minus q respectively. The spheres are placed touching each other as shown in the figure. If the potential at the center of the sphere A is VA and that of B is VB, then what will be the potential difference A and B? So we have to first see what is the potential due to uniformly charged dielectric sphere. Let's see. Answer 5. Uniformly charged dielectric sphere. Uniformly charged dielectric sphere. So if you have a uniformly charged dielectric sphere, of radius capital R and charge Q is uniformly distributed throughout the volume, so that charge density rho is Q by 4 by 3 pi RQ. So in this situation, what will be potential outside R greater than R? So you can easily find this potential. So you will see that potential is simply if you assume all charges are centered at this point, at the origin, at the center of the dielectric sphere. So potential is given by 1 by 4 pi epsilon naught Q by R. This will be the potential. This is potential outside. And what will be potential inside? You can easily calculate using the definition that VR is minus infinity to R E dot dl. So that you can easily calculate. And similarly, if you calculate potential at the center, this will be given by 3Q by, you can easily verify this, 8 pi epsilon 0 R. This is any point inside and this is any point outside. So because if you have more than one charge, so then you have to find the potential due to individual charges and then take a scalar sum. So here you have a two dielectric spheres. So if you are considering these two dielectric sphere, this is the center A and this is the center B, and this contains plus Q charge, this contains minus Q charge, and they are separated by a distance 2a. This will be 2a. So what will be potential at A? So point A is at the center of this sphere, but also 2a distance away from B. So at the center, potential at A will be given by, this is at the center of plus Q. So this is given by 3Q by now this potential will be given by this is the radius. Here you have to write the radius. This will not vary, it's some fixed value. So this, its radius is capital R. So potential at the center is 3Q by 8 pi epsilon 0 R, where R is the radius of the dielectric sphere. So this formula you have to remember, otherwise you have to derive it. So now see, this point. So this is plus 3q by 8 pi epsilon naught A. And this is 2a distance away from minus q charge. So I will use this formula. Minus q by 4 pi epsilon 0. And this r will be 2a. R will be 2a. Yes or no? So this is 3q minus q is 2q. So what will be VA? VA is 1 by 4 pi epsilon naught q by A. This is potential at the center of dielectric sphere A. Now you have to find potential at the center of dielectric sphere B. So at this point, what will be VB? Now this is at the center of minus q charge. So here you will write minus 3q because radius is same. So 8 pi epsilon naught A plus q by 4 pi epsilon naught 2a. And then VB will be minus q by 4 pi epsilon naught A. This is VB. So you know VA and VB, and if you take the difference, VA minus VB, A minus B, so 2q, so this will be q by 2 pi epsilon naught A. So if you take this difference, q by 2 pi epsilon naught A. So at least in this case, option is q by 2 pi epsilon naught A. So option C is correct here. So at least you should remember the field due to uniformly charged dielectric sphere and what will be potential due to uniformly charged dielectric sphere, because these are the standard result and you have to apply it. Otherwise, you have to derive it and it will take some time. So standard result you have to remember. Please note it down. So now let's take one more question. Now take question number 8. Take question number 8. So electric potential of some configuration is given by this expression. The charge density and the total charges are respectively. Now potential is given and you have to find the charge density and the total charge. So let's see. So if you know electric field, then you can use differential form, divergence C rho by epsilon naught. Now see question number 8. So in this case, E is given by minus of gradient V. Now there is a spherical symmetry. It is given in terms of R. So take an spherical symmetry. So what will be the electric field? So this is given by minus of del V by del R cap, and this will be, put the value of A, so this is minus A del R, and this is e power minus lambda R by R into R cap. ठीक है? So let's differentiate it. So E is given by minus A. So you have R exponential differentiate numerator. So this is denominator into differential of this, and this will be minus lambda minus into 1 by R square R cap. Is it clear? So now this will be given by, E is given by, this is lambda times A exponential e power minus lambda R is common. Then you will get, multiply with minus, so you will get 1 plus lambda R cap by R square. So this will be the electric field. And you have to always see, whenever you are getting R cap by R square, and if you are taking the divergence, you will get the Dirac delta function. So charge density is given by, charge density rho is given by epsilon naught divergence of E. Charge density is epsilon naught divergence of E. And you know, you have a scalar into vector. This term is a scalar and this is a vector. So you have to use the product rule for divergence. So this will be given by epsilon naught A. You will write here e power minus lambda R 1 plus lambda R. Because divergence E is a scalar. So next second term will be divergence of R cap by R square plus R cap by R square dot, you have to take gradient, dot gradient exponential minus lambda R 1 plus lambda R. So let's calculate this. And you know, divergence R cap by R square is 4 pi Dirac delta function. So use that result. So this will give you charge density rho is given by epsilon naught A. This is 4 pi delta function. So I'm writing here 4 pi 3-dimensional Dirac delta function. Because it's a special vector, it will be 0 except at one point. And then you should write here e exponential minus lambda R 1 plus lambda R. So this will be first term. And if you check for, if you find the gradient of this value, so I'm writing the result, you should verify it, R cap by R square. This value will be dot, this will be given by minus lambda square. You can easily check gradient of this value, R e power minus lambda R cap. This is the gradient, this value you can check. Minus lambda square R exponential minus lambda r cap. So if you take dot product, this r dot r is 1, this will cancel out. So what you will get, let's see. Now I have taken epsilon naught a common here. So this is 4 pi and four pi. Now see, if you take, because delta function is defined at r is equal to 0 only. Because delta function is defined at r is equal to 0 only. So we can put r is equal to 0 here. So if you put r is equal to 0, this value will be 1. So that's why I am writing here only 4 pi Dirac delta function. For charge density, I am taking this value to be 1 because when you put r is equal to 0, this will be 1. And this is minus lambda square by r exponential minus lambda. So this will be the charge density. Because by definition, Dirac delta function, this will be 0 if r is not equal to, if r is equal not equal to 0. And this will be infinity when r is equal to 0. At r is equal to 0, this value will be infinitely high. And at all other point, this value will be 0. So that is the Dirac delta function. So because it is non-zero at r is equal to 0 only, so this will take simply the function value. So that's why you can put r is equal to 0. Clear? So I have substituted because for all other value it will be 0. But at r is equal to 0, it can take the function value. This is the function fr. So you can put r is equal to 0. So that's why I have written here 4 pi delta r, because exponential e power minus 0 is 1. This is also 1 plus 0 is 1. So you will get 1. And now once you know the charge density, you can find the total charge. So let's see what will be the total charge now. So in this situation, we have to see the total charge. So total charge is given by Q enclosed is rho d tau. Q total will be given by volume integral rho d tau. So rho we have already calculated. So let's see that you are writing here epsilon naught a. First term is 4 pi Dirac delta function. So this will be given by 4 pi delta r d tau. And you have to integrate in whole space minus lambda square exponential e power minus lambda r by r into d tau, and d tau is 4 pi r square dr, and this will be 0 to infinity, all space. And we know the property of delta function that this value will be always 1. So total charge is given by epsilon naught a. This value is 1. So you will get here 4 pi. Now this is what? Minus lambda square minus lambda square into 4 pi, and then you have 0 to infinity r e power minus lambda r dr. Let's check this integral value. So this will be given by epsilon naught a 4 pi minus 4 pi lambda square and what will be this integral? Let's see uv1. So I am taking this result, integral uv dx. If u and v is function of x, so this is uv1 minus u dash v2 plus u double dash v3 and so on. So this is u dash is derivative of u, v1 is integral of v. So this will give you r, and integral of this will be exponential minus lambda r by minus lambda minus u dash 1, and then integral of this e power minus lambda r by lambda square 0 to infinity. So if you take infinity, this tends to 0. And if you take r is equal to 0, you will get 1 by lambda square. So by taking this integral, you will get epsilon naught a 4 pi minus 4 pi lambda square. So e power minus infinity tends to 0. So you are getting 0. And then if you put 0 minus of, put r is equal to 0. So this is 0 minus 1 by lambda square. So now you will get epsilon naught a 4 pi. This will be plus. So this is minus 4 pi. So total charge in whole space, if you calculate with this charge density, it will be 0. So in this case, option A is correct. So in question number 8, option A is correct. So it's a matter of calculation. If you remember the formulas and if you know the concept, then it's all about calculation. And just see in this question, because it is V, so you have to find E, then you have to find divergence. Divergence of r cap by r square is Dirac delta function. So you have to use all those concepts. So that's why you need lots of calculation in questions. So if you practice these questions, you will get similar type of calculation in exam. So that's why we are focusing on these questions, that once you solve this question, you will be able to build speed and accuracy. And you should also avoid the silly mistakes. So that's why must solve all questions that are given in our QIP file. Is it clear? So that is all about from today's C.T.P series. In next lecture, we will take some question on potential and also on electrostatic energy, and then about conductors. Clear? Okay then. Thank you. Thank you everyone. Thank you.